A point exists where gravity shatters reality itself. This is the Celestial Singularity, a tier in the cosmos where time, space, and mystery violently converge. Stephen Hawking reminded us that the universe does not allow perfection, and this idea lies at the heart of our journey. By the end, you will see the cosmos through an entirely new lens, understanding how black holes warp existence and what secrets lie at their impossible cores. We will explore where the laws of physics break down and confront the possibility of wormholes bridging distant stars. What does it truly mean to approach a place where time itself stands still? This voyage will challenge everything you assume about the universe. Are you ready to question the very nature of reality? Gravity's final victory is absolute. Envision a star, once a brilliant furnace, finally succumbing to its own immense weight. It collapses inward, falling forever into itself, until all that mass is compressed into a point of zero volume. This is the singularity, a cosmic paradox where density becomes truly infinite. The very fabric of spacetime warps to an extreme that our mathematics can describe, but our minds cannot truly grasp. This idea emerged directly from Einstein's theory of general relativity, which predicted that under such immense gravitational force, matter has no other fate. It is crushed beyond the realm of atoms, beyond the particles we know, into a state that simply defies all known physics. At this point, the equations break down. The rules of the universe, as we understand them, simply stop working. The renowned physicist Roger Penrose referred to this boundary as the end of time itself, a point beyond which no future exists for anything that crosses it. This is not merely a distant mathematical curiosity. At the heart of our own Milky Way galaxy, within the supermassive black hole known as Sagittarius A star, lies such a singularity. Its immense gravity, generated by millions of suns compressed into an infinitesimal point, dictates the orbits of stars light years away. We cannot see this singularity directly, of course. It is hidden from our view by the event horizon, a one-way boundary in space. Think of this horizon as the ultimate point of no return. Once anything, even light, crosses this invisible threshold, it is lost forever to the singularity, severed from our observable universe. This shielding is why we can study black holes from a distance, mapping their gravitational influence, while the true heart of the mystery remains permanently veiled. What does it mean that our cosmos is built upon such foundations, that existence allows for places where reality itself simply ends? To stand at the edge of such an abyss is to confront the ultimate limits of human knowledge. These cosmic whirlpools are the primary gateways to the singularity, a one-way journey into the ultimate unknown. Picture a vortex in space so powerful it pulls everything into its depths with no chance of return. This is the nature of a black hole, a natural laboratory where we can test the very limits of physics. The idea first gained real traction with Carl Schwarzschild, who found a solution to Einstein's equations that described regions of spacetime from which nothing, not even light, could escape. His work revealed the inevitability of these gravitational traps. Physicists like Kip Thorne have since shown us how profoundly these objects warp reality. They stretch time itself so that a single second for someone falling in could be an entire eon for an observer watching from a safe distance. To understand this journey, we must first break down the structure of a black hole. The outermost feature we can see is the accretion disk, a superheated whirlpool of gas and dust spiraling inward at nearly the speed of light. This glowing ring of matter is the last stop before the point of no return, the event horizon. Cross this invisible boundary and you are severed from the universe forever. destined for the singularity at the core, but not all black holes are the same. Stellar black holes form from the violent deaths of massive stars in supernova explosions, collapsing a star several times heavier than our Sun into a point just a few miles across. Supermassive black holes, millions or even billions of times the mass of our Sun, lurk at the centers of galaxies, their origins perhaps tied to direct collapse of vast gas clouds in the early universe. There may even be primordial black holes, tiny relics forged in the first chaotic moments after the Big Bang. The first direct image of a black hole, captured by the Event Horizon Telescope, brought this cosmic architecture into stunning focus. It showed us the dark shadow of the supermassive black hole in galaxy M87, silhouetted by the fiery glow of its own accretion disk. This shadow is not the event horizon itself, but the ghostly imprint of the black hole's immense gravity, bending light and trapping it within an inescapable prison. This image confirmed our theories, yet it also deepened the mystery. It forces us to ask a profound question, one that has puzzled physicists for decades. What happens to all the information about an object that falls into a black hole? According to the rules of the universe, information cannot be truly destroyed, yet according to a black hole, it is lost forever behind the event horizon. This is the information paradox, a fundamental conflict between gravity and quantum mechanics that pulls us toward the next great enigma. That burning book, its information seemingly lost forever, is a powerful echo of one of the most profound puzzles in physics. This is the information paradox, a conflict that strikes at the very foundation of our understanding of reality. Stephen Hawking first proposed this dilemma, suggesting that when a black hole evaporates through the process now known as Hawking radiation, all the information about the objects that fell into it could be permanently erased. Think of a black hole swallowing a star. That star had a specific composition, a temperature, a history. All of that is information, and according to the core rules of quantum mechanics, that information can never be truly destroyed. It can be scrambled, but it must, in principle, be recoverable. Hawking's initial work suggested that black holes break this fundamental law. The radiation leaking from a black hole, he argued, was entirely random and thermal, carrying no imprint of what was consumed. If correct, this would mean the universe has a severe case of amnesia, and the past becomes fundamentally unknowable. This idea did not sit well with many physicists, including Leonard Susskind, who fiercely defended the sanctity of information. Their debate led to a remarkable proposal, the Holographic Principle. This mind-bending concept suggests that all the information describing the three-dimensional volume of a black hole is actually encoded on its two-dimensional event horizon, like a cosmic DVD. The surface area of the horizon, not the volume it contains, determines the black hole's maximum information storage capacity. This principle introduces the concept of entropy, a measure of disorder, into black hole physics. Just as a melted ice cube has higher entropy than a solid one, a black hole is considered the object with the highest possible entropy in any given region of space. The page time, a concept developed by physicist Don Page, marks a crucial turning point in a black hole's life. It is the moment when the black hole has evaporated enough that the information it began emitting long ago starts to leak back out, scrambled but preserved. This leads to an even more startling possibility, the Firewall Paradox. If information is preserved on the horizon, what does an astronaut experience when crossing it? The principles of general relativity say they should feel nothing, passing smoothly into the black hole's interior. But quantum mechanics suggests that to preserve information, the event horizon must be a searing wall of high-energy particles, an instant and violent end. This paradox highlights the raw, unresolved conflict between our two most successful theories of the universe. Resolving it is the primary goal of theories like string theory, which attempts to describe all particles and forces as tiny, vibrating strings. Some string theory models suggest black holes are not eternal prisons but rather tangled knots of spacetime, potentially connecting to other regions of the cosmos. This contemplation of information, and whether it can be lost or merely transformed, pulls our gaze from the destructive heart of the singularity toward a more constructive, yet equally mysterious possibility. Could these cosmic knots be bridges to another place or time? These bridges through space-time offer a breathtaking escape from the crushing finality of the singularity. A wormhole is a cosmic shortcut, a theoretical tunnel that could connect two distant points in the universe by folding the fabric of reality. The mathematics of Einstein's general relativity allows for such a structure, often visualized as a tunnel with two mouths linked by a throat. One mouth could be here in our solar system, while the other might reside near a star thousands of light years away. Stepping through would be like finding a secret passage through a mountain, bypassing the long and arduous journey over the peak. This idea was first explored by physicists Albert Einstein and Nathan Rosen, who discovered that the equations describing a black hole singularity could be extended to form a bridge to another region of spacetime. For a long time, these Einstein-Rosen bridges were considered mere mathematical curiosities, utterly impassable and collapsing instantly. Then, the visionary Carl Sagan, while writing his novel Contact, sought a scientifically plausible method for interstellar travel. He consulted physicist Kip Thorne, who took up the challenge and explored whether a traversable wormhole could exist. The answer was a tentative yes, but with one monumental catch. Keeping a wormhole's throat open against the force of gravity, which wants to pinch it shut, requires a substance known as exotic matter. This is not just unusual material, but matter that possesses negative energy density, something that pushes gravity apart rather than pulling it together. One potential source for this exotic energy is found right here on Earth in a quantum phenomenon called the Casimir effect. When two perfectly smooth, uncharged metal plates are placed extremely close together in a vacuum, they are pushed toward each other by a mysterious force. The space between the plates has less energy than the space outside, creating a region of negative energy that could, in theory, be harnessed to prop open a wormhole. But the implications of a stable wormhole are even more staggering than fast travel across space. If one end of the wormhole were moved at a significant fraction of the speed of light, or placed near a powerful gravitational field, time would flow at different rates at each mouth. Stepping through could send you not just to another location, but to another time entirely. This immediately raises the infamous grandfather paradox. If you traveled back in time and prevented your own grandfather from meeting your grandmother, how could you ever have been born to make the journey in the first place? This paradox challenges the very logic of cause and effect, suggesting that the laws of physics might actively prevent such time travel to protect the consistency of the timeline. The film Interstellar brought a visually stunning and scientifically informed depiction of a wormhole to a global audience, presenting it as a shimmering sphere warping the star field behind it. This portrayal, guided by Kip Thorne's expertise, helped ignite public fascination with the real science behind these cosmic portals. Yet, for all their theoretical promise, wormholes remain shrouded in profound uncertainty. Could they be the key to understanding the true nature of singularities, transforming them from endpoints into gateways? To answer that, we must venture even closer to the edge of reality and confront the ultimate warping of time itself. An astronaut in a stable orbit around a black hole would witness a universe aging at an impossible speed. Years, decades, even centuries on Earth could flash by in what feels like mere minutes for the observer suspended in that immense gravitational field. This is not science fiction, but a direct consequence of Einstein's theory of relativity, a phenomenon known as time dilation. Where gravity is strongest, time itself flows more slowly. This warping of time becomes truly extreme as you approach a singularity, where the gravitational field is so intense that clocks would appear to slow to a crawl and then stop entirely at the event horizon. The formulas that describe this are startlingly direct. Gravitational time dilation tells us that a clock closer to a massive object will tick slower than a clock farther away. The effect is compounded by velocity. The faster you move through space, the slower you move through time, a result confirmed by the famous Hayfel-Keating experiment where atomic clocks flown on airplanes returned showing measurable, tiny delays compared to clocks that remained on the ground. This leads to the classic twin paradox. Imagine one twin blasts off on a high-speed journey to a nearby star while the other remains on Earth. Upon return, the traveling twin would be younger than the sibling they left behind, their personal timeline having stretched out relative to Earth's. We already account for this reality in our daily lives. The Global Positioning System, or GPS, relies on a network of satellites orbiting our planet. These satellites experience both velocity-based time dilation from their speed and gravitational time dilation from being in a weaker gravitational field than Earth's surface. If the satellite's incredibly precise clocks were not constantly adjusted for these relativistic effects, the entire system would become useless within hours, with location data drifting by several miles each day. On a cosmic scale, we can observe this phenomenon around supermassive black holes. Astronomers have watched stars make close passes around Sagittarius, a star, and their light stretches to redder wavelengths as they fight the black hole's gravity, a telltale sign that time is slowing down for the star from our distant perspective. How does this fundamental distortion of time challenge our perception of reality? It shatters the idea of a single, universal now. Your now and my now are only synchronized if we share the same gravitational and velocity context. The flow of time is not a river moving at the same speed for everyone, but a personal experience intimately woven into the fabric of the space-time you occupy. This forces us to confront a strange truth, that the past, present, and future might be more fluid and interconnected than our everyday senses can perceive. If time can slow to a standstill, what does that imply about the nature of existence within that frozen moment? This question leads directly to one of the most intriguing proposals in theoretical physics, a concept designed to protect the sanctity of our universe from the chaotic implications of a naked singularity. Our universe seems to have a built-in modesty clause, a rule that forbids its most chaotic cores from ever being seen. This is the cosmic censorship hypothesis, a profound idea from Roger Penrose suggesting that nature always wraps a singularity in the protective shroud of an event horizon. It is as if the cosmos itself deems these points of infinite density too dangerous, too unpredictable to be left exposed. A naked singularity, one without its event horizon, would be a tear in the fabric of reality with no curtain drawn. The laws of physics as we know them would break down not in some hidden interior, but right out in the open for the entire universe to see. Cause and effect could unravel, and predictability would vanish. The cosmic censorship hypothesis comes in two forms. The weak version suggests that while a naked singularity might theoretically form from a perfectly tuned collapse, any real-world, slightly imperfect event would always produce an event horizon to hide it. The strong version is far more absolute, stating that the laws of physics simply forbid naked singularities from ever forming under any circumstances. Mathematicians like Demetrios Christodoulou have delved into the extreme physics of gravitational collapse, running complex numerical simulations to test the limits of this censorship. Their work explores whether certain conditions, like an impossibly rapid collapse or a very specific distribution of matter with intense rotation, could overwhelm nature's tendency to veil the singularity. Angular momentum is a key player here. Just as a spinning ice skater pulls their arms in to spin faster, a collapsing star with enormous spin might not be able to form a horizon before its core is crushed into a singularity, potentially leaving it naked. Imagine a scenario where ultra-high-density matter, unlike anything we know, collapses in just the right way. Instead of forming a black hole, it could theoretically expose its central singularity to the outside universe. What would we see? The mathematics suggests a maelstrom of unpredictable forces, where gravity could fluctuate wildly and time could become chaotic. This is not just a mathematical curiosity. The integrity of our entire understanding of physics rests on the idea that the universe is predictable, that if you know the initial conditions of a system, you can calculate its future. A naked singularity shatters that principle. It creates a region where the past no longer determines the future, where calculations become impossible. So we are left with a haunting question. Is cosmic censorship a fundamental law of nature, or is it a temporary shield that might be pierced by a deeper truth? The answer may lie in the quantum realm, where the very concepts of singularities and event horizons might dissolve into something even stranger. The laws of physics seem to demand a cosmic censor, but what if the singularity itself is an illusion? Our theories break down at that point because we are trying to describe the quantum realm with the rules of classical gravity. To truly understand the heart of a black hole, we must weave together two seemingly incompatible tapestries, general relativity and quantum mechanics, into a single fabric known as quantum gravity. General relativity paints a beautiful picture of the cosmos on a grand scale, where gravity is the curvature of smooth, continuous spacetime. Quantum mechanics reveals a frantic, probabilistic world of tiny particles and discrete packets of energy. Both are spectacularly successful in their own domains, but they become enemies at the singularity. Here, the immense gravity of general relativity meets the infinitesimally small quantum world, and our mathematical descriptions explode into meaningless infinities. To resolve this, we must discover the fundamental building blocks of spacetime itself. This is the monumental quest of quantum gravity. One of the most prominent approaches is string theory. It proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating strings. An electron is a string vibrating one way, a quark another, and the force of gravity would be carried by a hypothetical particle called the graviton, a string vibrating in yet another specific pattern. In this framework, the harsh singularity of a black hole might be replaced by a fuzzy, vibrating ball of strings, a fundamental object that avoids the infinite density problem altogether. Another compelling path is loop quantum gravity, championed by physicists like Carlo Rovelli. This theory suggests that spacetime itself is not smooth and continuous, but is woven from a network of finite, discrete loops. Think of the fabric of reality as a chainmail tunic, not a seamless silk sheet. This granular structure has a profound implication. It prevents matter from collapsing into an infinitely dense point. Instead of a singularity, a collapsing star could experience a quantum bounce. The crushing gravity would reach a maximum force and then rebound, potentially spewing matter out into a new region of spacetime, or even giving birth to a new universe. This idea has been applied to the origin of our own cosmos, suggesting the Big Bang was not a true singularity, but a great bounce from a previous contracting universe. Merging these worlds is not easy. A major hurdle is renormalization. In quantum field theory, calculations often produce annoying infinities that must be carefully subtracted to get a sensible answer. For gravity, this process fails completely. The infinities are too powerful to remove. This is a clear signal that we are missing a deeper, more complete theory. The holographic principle, which we encountered with black hole information, becomes a crucial guide here. It suggests that a description of a volume of space, including all the particles and forces within it, can be perfectly encoded on its lower dimensional boundary. A powerful realization of this is the AD-SCFT correspondence. It provides a mathematical dictionary that translates problems in a hypothetical gravity-filled universe into problems in a quantum field theory without gravity living on its boundary. This allows physicists to use a well-understood quantum system to probe the mysterious nature of gravity and black holes, turning an impossible calculation into a tractable one. So how might quantum gravity ultimately rewrite the story of the singularity? It could transform it from a destructive endpoint into a transformative gateway. The infinite curvature predicted by Einstein might be a mirage, a sign that our classical equations have reached their limit. In its place, we could find a dynamic quantum structure that links our universe to others or represents a cosmic reset. The journey to this deeper reality leads us to the ultimate singularity, the one from which everything we know supposedly emerged. The ultimate singularity lies not in a distant black hole, but at the very beginning of everything. Our entire observable universe, all the galaxies, stars, and planets, was once compressed into an infinitesimal point of infinite density and temperature. This is the primordial singularity of the Big Bang, the moment when space itself began to expand and time began to tick. The concept was first proposed by Georges Lemaitre, a physicist and priest who called it the primeval atom. He envisioned the cosmos erupting from this single, incredibly dense state. Decades later, Stephen Hawking applied the mathematics of singularities to this beginning, showing how general relativity inevitably points back to a moment of infinite curvature. The evidence for this explosive origin is etched across the sky. The cosmic microwave background radiation is the faint, leftover heat from that initial fireball, a cosmic echo that fills every direction of space. This afterglow was predicted and then accidentally discovered, providing a cornerstone for the Big Bang model. But what happened in the very first moments? To understand that, we must venture into the Planck epoch, a period so brief it is almost beyond time itself. This is the first fleeting fraction of a second after the singularity, where the universe was smaller than a single atom and the four fundamental forces were likely unified into one. Our current laws of physics simply cannot describe this realm, as quantum gravity would have reigned supreme. Then came a dramatic event known as cosmic inflation. The universe underwent a period of exponential expansion, doubling in size repeatedly in an unimaginably short time. This inflationary period stretched the microscopic quantum fluctuations of the Planck epoch, magnifying them into the seeds for all future cosmic structure. The tiny ripples in density became the gravitational wells that would eventually pull matter together to form the first galaxies, clusters, and superclusters. This is where the James Webb Space Telescope enters the story. By peering back to the universe's infancy, it has observed galaxies that formed shockingly early, much sooner than some models predicted. These ancient, fully formed galaxies are forcing cosmologists to refine the timeline of cosmic evolution, challenging our understanding of how quickly structure emerged from the primordial soup. Yet the singularity at time zero remains a profound problem. General relativity breaks down completely, yielding nonsensical infinities. To address this, Hawking and James Hartle proposed the no-boundary proposal. This elegant idea suggests the universe has no singular beginning point in time, much like the North Pole has no edge. If you travel back in time, the dimension of time smoothly transforms into a dimension akin to space, creating a finite but unbounded cosmos with no need for a boundary or a singular start. This leads to the most profound question of all: what existed before the Big Bang? If time itself began with the universe, the question may be meaningless. Yet our curiosity pushes us to consider alternatives, theories that seek to replace the singular birth with a more complete cosmic story. The Big Bang Singularity may not be a one-time creation event, but a single beat in a cosmic heartbeat. Picture universes expanding, contracting, and rebounding in an endless, rhythmic loop. This is the core of cyclic cosmology, a vision where our entire cosmic history is just one chapter in an infinite book. The ekpyrotic universe model, developed by physicists like Paul Steinhardt, offers a compelling alternative to a singular beginning. It proposes that our Big Bang was the result of a colossal collision between two vast, sheet-like structures known as branes, existing in a higher dimensional space. Instead of erupting from an infinitely dense point, our universe was born from a transformative impact, a bounce that avoids the mathematical nightmare of a true singularity. This cyclic process elegantly solves classic cosmological puzzles. The horizon problem asks why the universe is so uniform in all directions, as if distant regions had once been in contact. The flatness problem questions why the geometry of our cosmos is so perfectly balanced, while inflation theory addresses these by proposing a rapid early expansion. Cyclic models offer a different path. In an endless cycle, each universe is stretched and smoothed over trillions of years, naturally achieving the flatness and uniformity we observe. A key player in this cycle is dark energy. That mysterious force accelerating the expansion of our universe today might be the very engine that sets the stage for the next cycle. As dark energy drives galaxies apart, it could eventually dilute matter and energy to near nothingness, preparing the cosmos for a great contraction. This leads to the concept of the Big Crunch, a hypothetical end where the universe stops expanding and collapses back in on itself under its own gravity. But instead of ending in a final, destructive singularity, this collapse could reach a maximum density and rebound in a new Big Bang, starting the cycle anew. Roger Penrose's conformal cyclic cosmology presents an even more mind-bending version of this loop. He suggests that as the universe expands to an unimaginably vast, empty state, its geometry can be mathematically rescaled to match the hot, dense geometry of the Big Bang. In this model, the end of one universe becomes the beginning of the next, with the passage of time between cycles losing all meaning. Penrose even proposes that evidence for this might be found in the cosmic microwave background, in the form of faint, circular imprints left by the gravitational waves of colliding supermassive black holes from a previous cosmic cycle. If our universe is part of such an eternal return, it forces us to confront a staggering possibility. Could this cycle be just one of countless others, each with its own unique laws of physics? This idea naturally spirals into the Multiverse Hypothesis, where singularities are not in points but the bridges between an infinite number of coexisting realities. Our universe could be one delicate thread in an infinite cosmic tapestry. This is the Multiverse Hypothesis, a vision of countless parallel realities, each with its own unique laws of physics. In some of these universes, singularities might be commonplace, while in others, the very conditions for black holes could be impossible. The concept emerges naturally from our most ambitious theories. Eternal inflation proposes that the rapid expansion of space never truly stops overall. but instead forms isolated pockets where inflation ends, each pocket becoming a separate bubble universe. Meanwhile, string theory's vast landscape suggests an almost innumerable number of possible stable vacuum states, each one corresponding to a different universe with its own distinct properties and physical constants. Cosmologist Max Tegmark has organized this dizzying possibility into a hierarchy of multiverses. Level 1 is simply our own universe extended infinitely, containing regions so far away that their light has never reached us, each with every possible variation of history playing out. Level 2 consists of those other inflationary bubbles, forever separated from us by an ever-expanding void, where even the fundamental constants like the strength of gravity could be different. Level 3 is the many worlds interpretation of quantum mechanics, where every possible outcome of a quantum event branches off into its own reality. The most profound is Level 4, which proposes that every mathematically consistent structure actually exists as a physical universe. This framework forces us to confront the Anthropic Principle. It simply states that we can only observe a universe capable of sustaining life. The constants in our cosmos, from the force of gravity to the mass of an electron, appear finely tuned to allow for stars, planets, and ultimately observers. In a multiverse, this fine-tuning loses its mystery. We do not live in a special universe, we simply inhabit one of the rare bubbles where the numbers happen to line up correctly for our existence. Yet this raises a formidable scientific challenge. If other universes are fundamentally disconnected from our own, how can we ever test their existence? Some scientists look for potential scars in our own cosmos. The search for specific patterns in the cosmic microwave background, like the telltale swirls of B-mode polarization that could be imprints from collisions with other bubble universes in the distant past, offers a tantalizing, though unconfirmed, pathway for evidence. This vast perspective reshapes our view of the celestial singularity. In our universe, a black hole is a monstrous in point, but in another reality with weaker gravity, singularities might be gentle, or perhaps matter collapses into entirely different structures we cannot imagine. The uniqueness of our singularities dissolves into a cosmic lottery. This contemplation of infinite possibilities inevitably draws our focus back to the invisible forces that dictate the structure of our own specific cosmic bubble, the mysterious dark components that govern the fate of everything we see. Most of the universe is made of things we cannot see. This invisible cosmos, composed of dark matter and dark energy, forms a hidden architecture that dictates how singularities are born and how they will ultimately meet their fate. The story of their discovery began with the meticulous work of astronomers like Vera Rubin. She studied the rotation of galaxies and found a profound anomaly. The stars at the outer edges of spiral galaxies were moving just as fast as those near the center. According to the laws of gravity, these outer stars should have been flung away into the void. The only explanation was that each galaxy was embedded within a vast, massive halo of something invisible, a substance that came to be known as dark matter. This mysterious matter provides the gravitational glue that holds galaxies together, a cosmic scaffold upon which visible stars and gas are draped. Its influence does not stop there. Dark matter halos are the nurseries for the universe's most massive singularities. As gas and dust are pulled into these halos by dark matter's gravity, they condense and feed the growing black holes at the centers of galaxies, allowing them to balloon into the supermassive monsters we observe today. The evidence became even more striking with observations of the Bullet Cluster, a cosmic collision of two galaxy groups. Here, the visible matter, in the form of hot gas, was slowed and separated from the bulk of the mass, which was mapped through gravitational lensing. This proved that dark matter is a real, physical substance that interacts primarily through gravity, passing through itself and normal matter like a ghost. Yet, despite accounting for about 25% of the universe, we still do not know what it is. Is it a new, undiscovered particle, a weakly interacting massive particle, or WIMP, that experiments deep underground and in colossal machines like the Large Hadron Collider are desperately trying to create and detect? Or is it something even more exotic? While dark matter pulls the cosmos together, dark energy works to tear it apart. This enigmatic force, discovered by observing distant supernovae and their surprising redshift, is causing the expansion of the universe to accelerate. It makes up nearly 70% of the universe's mass-energy budget, and its nature is arguably the greatest mystery in physics. Is it a constant energy inherent to the vacuum of space itself, a cosmological constant as Einstein once proposed? Or is it a dynamic field that has changed over time, known as quintessence? This relentless push has a direct and lonely consequence for singularities. As dark energy accelerates the expansion of space, galaxies will be pulled away from one another, eventually becoming isolated islands. Black holes will find fewer and fewer stars and gas clouds to consume, their growth stunted as they drift apart in an ever-cooling, ever-darkening cosmos. In a hypothetical extreme known as the Big Rip scenario, dark energy could become so dominant that it overcomes all other forces, tearing apart galaxies, then solar systems, then stars and planets, and ultimately the very fabric of spacetime itself, including every last singularity. So how do these dark components interact with the singularities they help create and will one day isolate? Their primary dialogue is through gravity, the same force that creates the black holes in the first place. The distribution of dark matter influences how and where black holes merge, and the accelerated expansion driven by dark energy will dictate the long-term fate of these cosmic behemoths. To truly listen in on this gravitational conversation, we need a new sense, a way to hear the universe. This ability arrived with one of the most monumental discoveries in modern science, the direct detection of ripples in spacetime. The universe finally revealed its voice. In 2015, after a century of searching, scientists at the LIGO observatory heard it, a faint chirp that was the first direct detection of gravitational waves. These are not waves of light or sound, but literal ripples in the fabric of spacetime itself, vibrations sent across the cosmos from the most violent events imaginable. When two massive objects like black holes spiral toward each other, their immense gravity churns the spacetime around them, sending out these distortions at the speed of light. It is like dropping two heavy stones into a still pond, the resulting ripples carrying the story of the splash across the entire surface. For decades, experts like Kip Thorne theorized that these waves would be our only way to truly hear the final moments before two singularities become one. The detection of these waves confirmed a key prediction of Einstein's general relativity and opened an entirely new window onto the universe, a gravitational sense to complement our telescopes. The generation of these waves is a product of extreme acceleration. Picture a binary black hole system, two dark voids locked in a final, frantic dance. As they orbit one another at nearly the speed of light, they whip the fabric of spacetime around them, emitting energy in the form of gravitational waves. This energy loss pulls them ever closer, tightening their orbit and increasing the frequency of the waves until they finally collide and merge in a single, cataclysmic event. The frequency of these waves is crucial for detection. Ground-based instruments like LIGO and Virgo are tuned to listen for the high-frequency chirps, around hundreds of cycles per second, produced by stellar mass black holes and neutron stars in their final seconds. But to hear the deeper, lower-frequency rumbles of supermassive black holes merging at the centers of galaxies, we need to go to space. Future observatories, like the planned LIS mission, will consist of multiple spacecraft flying in a precise formation millions of miles apart, effectively creating a gravitational wave antenna larger than the Sun's distance from Earth. The first signal ever heard, named GW150914, told a story of breathtaking power. It came from a pair of black holes, one about 36 times the mass of our Sun, the other 29, swirling together over 1 billion light-years away. In a fraction of a second, they merged into a single, more massive black hole. The energy released in that final instant was staggering, equivalent to 3 times the mass of our Sun converted directly into gravitational wave energy, briefly outshining every star in the observable universe combined. This event did more than confirm a theory. It provided profound insights into the nature of the singularities involved. By analyzing the waveform, the specific pattern of the ripple, physicists could infer the masses and spins of the black holes, testing whether their event horizons behaved as general relativity predicts. The clean, simple nature of the signal, free from the complex mess of colliding matter, told us we were witnessing pure gravity in action. What other secrets are encoded in these cosmic ripples? The same violent processes that create gravitational waves also power some of the brightest and most enigmatic objects in the cosmos, the dazzling beacons known as quasars. That brilliant lighthouse in the cosmic dark is a quasar, a beacon from the edge of time itself. These objects are not stars, but the incredibly bright hearts of young galaxies, shining with the power of 1 trillion suns. For all their brilliance, they are surprisingly compact, their energy generated in a region smaller than our own solar system. The discovery of quasars began as a mystery in the 1960s, when astronomers using radio telescopes found pinpoint sources of intense radio waves that looked like stars in visible light. They were given the name quasi-stellar radio sources, which was soon shortened to quasar. The real breakthrough came from Martin Schmidt at Caltech. He was studying the spectrum of a quasar known as 3C273, and he was baffled by the strange pattern of its emission lines. He suddenly realized he was looking at the familiar signature of hydrogen, but shifted dramatically toward the red end of the spectrum. This immense redshift meant the object was not a nearby star, but something fleeing from us at tremendous speed, billions of light-years away. To be visible from such a distance, it had to be emitting almost unimaginable amounts of energy. The only conceivable engine powerful enough was a supermassive black hole in the process of feasting. At the core of every quasar lies a supermassive black hole, millions or even billions of times the mass of our Sun. This gravitational monster is surrounded by an accretion disk, a swirling whirlpool of superheated gas and dust. As material spirals inward at nearly the speed of light, friction heats it to millions of degrees, causing it to glow with blinding intensity across the entire electromagnetic spectrum. But the spectacle does not end there. Perpendicular to the accretion disk, the black hole often fires out colossal jets of charged particles. These relativistic jets, traveling at a fraction of the speed of light, can stretch for hundreds of thousands of light-years into intergalactic space. When one of these jets is pointed almost directly at Earth, the quasar appears even brighter, an effect that makes them visible across the vastness of the cosmos. The Hubble Space Telescope and the Chandra X-ray Observatory have peered into these energetic hearts, resolving the structures around distant quasars and confirming their role as galactic engines. Quasars are not just cosmic curiosities, they are time capsules. Because their light has traveled for billions of years to reach us, we see them as they were when the universe was young. They were far more common in the early universe, a sign that supermassive black holes grew rapidly by consuming enormous amounts of gas. This frenzied eating shaped the galaxies that formed around them. The energy blasting from a quasar can regulate star formation, blowing away gas that would have otherwise collapsed into new stars and fundamentally influencing the size and structure of its host galaxy. The first identified quasar, 3C273, became a crucial ruler for measuring cosmic distances. Its immense and steady luminosity provided a standard candle, allowing astronomers to map the scale of the universe with new precision. So how do these brilliant beacons illuminate the behavior of the hidden singularity at their core? We cannot see the singularity itself, but the quasar is its voice. The flickering of a quasar's light tells us about the chaotic flow of matter just outside the event horizon. The power of its jets reveals how the black hole's spin can tap into immense reservoirs of energy, acting like a cosmic dynamo. A quasar is the most visible manifestation of a singularity's gravitational dominance, a temporary, brilliant firestorm that reveals how these dark hearts build the cosmic structures we see today. This exploration of brilliant, active singularities naturally leads us to consider their quieter, more rhythmic counterparts, the celestial lighthouses known as pulsars. A dead star spins faster than a kitchen blender, its rhythm so perfect it rivals the most precise atomic clocks on Earth. These are pulsars, the universe's natural lighthouses, born from the violent death throes of massive stars. When such a star explodes in a supernova, its core collapses under its own immense gravity. If the remaining mass is between 1 and about 3 times that of our Sun, the collapse halts, crushed into a city-sized sphere of pure neutrons. This is a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. It is a state of matter pushed to its absolute limit, a condition that falls just short of the infinite density of a singularity. The discovery of the first pulsar in 1967 by Jocelyn Bell Burnell was a moment of pure astonishment. She detected a radio signal from deep space that pulsed with such metronomic regularity that it was initially nicknamed LGM for Little Green Men. It was Anthony Hewish, her supervisor, who would later share a Nobel Prize for this revolutionary find, which opened an entirely new field of astrophysics. The incredible pulse comes from the star's intense magnetic field, which funnels radiation into beams from its magnetic poles. As the star rotates, these beams sweep across space, and if one crosses Earth's path, we observe a flash, a cosmic strobe light. The fastest of these, known as millisecond pulsars, can spin hundreds of times every single second, accelerated to dizzying speeds by siphoning material from a companion star. This precise timing makes them invaluable tools. By monitoring networks of these pulsars across our galaxy, scientists have created a gravitational wave telescope the size of the Milky Way itself. These pulsar timing arrays watch for minuscule, correlated shifts in the pulse arrival times, distortions that could be caused by long wavelength gravitational waves from merging supermassive black holes. One of the most powerful laboratories for testing gravity is the double pulsar system, where 2 pulsars orbit each other. This unique pairing allows for exquisitely precise tests of Einstein's general relativity. By measuring how their orbits decay as they radiate energy away in gravitational waves, physicists have found predictions and observations match with near-perfect agreement. So are these ultra-dense neutron stars the final step before matter surrenders completely to a singularity. They represent the ultimate standoff, where the quantum pressure of neutrons resists the crushing force of gravity. But if just a little more mass were added, that delicate balance would shatter. The neutrons would be overcome, and the collapse would continue. plunging past any known state of matter into the infinite density of a black hole singularity. Pulsars are the last sentinels at the edge of that abyss, showing us the ultimate fate of matter under pressures we can barely comprehend. A single sugar cube of this material would weigh more than every person on Earth combined. This is the reality of a neutron star, matter pushed to the very brink of oblivion. It is the final, desperate stand against gravity's ultimate victory. A city-sized sphere where the core of a dead star is compressed into a state akin to a single, gigantic atomic nucleus. The existence of such an object was only possible thanks to the foundational work of Subrahmanyan Chandrasekhar, who calculated the precise limit, now known as the Chandrasekhar limit, beyond which the quantum pressure of electrons can no longer support a star's core. For a neutron star, this concept is taken even further, held aloft by the fierce repulsion between neutrons themselves. Peering inside reveals a layered world of unimaginable extremes. The surface is a crust of iron, forged in the star's final moments, but just beneath lies a lattice of atomic nuclei drowning in a sea of free electrons. Deeper still, we reach the inner crust, where the pressure is so intense that protons and electrons are forced together, merging into neutrons. At the very heart of the star lies the core, a place of pure mystery. Here, matter may cease to be recognizable. Neutrons might flow without friction as a superfluid, a perfect liquid with zero viscosity, or they might dissolve entirely into a soup of their constituent parts, a seething ocean of free quarks and gluons known as quark-gluon plasma. This internal turmoil manifests in dramatic ways. Pulsars, those spinning neutron stars we met earlier, sometimes experience a starquake, a sudden cracking of their rigid crust that releases more energy than the brightest solar flare. This can cause the star's spin to suddenly increase, an event called a glitch, providing a direct seismic reading of the violent forces churning within. These stars are not just cosmic curiosities, they are the universe's ultimate forges. When two neutron stars spiral together and finally merge, the cataclysm is unlike any other. The event known as GW170817 provided the proof. In 2017, gravitational wave observatories felt the ripples of such a collision, and telescopes across the globe swiveled to see the aftermath. They witnessed a kilonova, a brilliant explosion that painted the cosmos with newly forged elements. This single event confirmed that the vast majority of the universe's heavy elements, including the gold in a wedding ring or the platinum in a catalytic converter, are created in these violent neutron star mergers, a process called rapid neutron capture, or the R process. But what happens if you add just a little more mass to this precarious balance? The neutron star's internal pressure, no matter how exotic, is overwhelmed. The star continues its collapse, vanishing behind an event horizon and giving birth to a new black hole singularity. This inevitable fate forces us to wonder, is a black hole the only possible outcome? Or could matter find an even more bizarre state of existence, creating something stranger still at the very edge of reality? Such a star would not collapse into a black hole at all. It would instead transform into something entirely new, an exotic star built from materials far stranger than anything in our periodic table. These are not mere neutron stars, but theoretical objects like quark stars or boson stars, cosmic entities that might use unknown physics to resist the final descent into a singularity. The concept of a quark star arises from the strange matter hypothesis proposed by physicists like Paul Heinzel. It suggests that under the immense pressure inside a collapsing star, the neutrons themselves might break down into their constituent parts. The protons and neutrons would dissolve, creating a soup of free quarks, including the elusive strange quark. In this bizarre state, up, down, and strange quarks could form a new, perfectly stable phase of matter, more fundamental than the atomic nuclei we know. This strange matter would be the ultimate ground state of reality, preventing further collapse and creating a star with a perfectly smooth surface, denser than a neutron star but without an event horizon. How could we ever spot such an object? Its emission signature would be unique. A quark star would likely cool much faster and emit more X-rays and gamma rays than a neutron star, its surface radiating the energy of its seething quark-gluon interior. Even more ethereal is the boson star, a giant sphere not of matter as we know it, but of force-carrying particles. Held together by its own gravity, a boson star could be transparent and nearly invisible, or it could be massive enough to mimic a black hole's gravity without the central singularity, a dark object with no event horizon to hide its core. The key to confirming their existence lies in the ripples of spacetime. When two exotic stars merge, the gravitational wave signal would have a distinct fingerprint, different from the clean chirp of black holes or the richer, more complex signal of colliding neutron stars. Astronomers once thought they had found a candidate in the neutron star RxJ 1856.53754. Observations suggested it was smaller and denser than any known neutron star should be, hinting it might be the first known quark star. Further study, however, indicated it was likely a very hot, ordinary neutron star with a different atmospheric structure, but the search continues. Could these exotic stars be the universe's way of showing us a path beyond the singularity? They represent a cosmic refusal to surrender to infinite density, suggesting that matter can find a stable, if utterly alien, state at the very edge of existence. This defiance against collapse is governed by more than just density. It is shaped by another invisible and titanic force, the immense magnetic fields that can warp the fate of stars themselves. Invisible lines of force weave through the cosmos, guiding the flow of plasma and sculpting the very environments where singularities reside. These magnetic fields are the silent architects of cosmic violence, playing a decisive role in how matter behaves in its final moments. The science that describes this intricate dance is magnetohydrodynamics, a field pioneered by Hans Alfvén, which explains how magnetic fields interact with ionized gases or plasmas. These fields are not static, they are generated and amplified by colossal dynamo effects, where the rotation and convection of stars and galaxies act like giant generators, spinning magnetic energy into existence. Nowhere is this more potent than in the superheated chaos of an accretion disk around a black hole. As ionized gas spirals inward at near light speed, the magnetic field lines are stretched and twisted into a frenzied web. This process does two remarkable things. First, it acts as a cosmic brake, transferring energy and allowing matter to lose momentum and fall toward the event horizon. Second, it funnels some of this infalling material into those spectacular, high-speed jets that blast away from the black hole's poles, channeling energy across thousands of light years. We can measure these invisible forces by observing the polarization of light. As light travels through a magnetized region, its waves become aligned in a specific direction, a telltale signature that allows us to map fields we can never touch. The Planck satellite has done exactly this for our own Milky Way, revealing a vast, filamentary magnetic scaffold that guides not only dust and gas, but also the paths of high-energy cosmic rays. This magnetic architecture influences everything, from the birth of new stars within interstellar clouds to the ultimate evolution of entire galaxies. So, how does this force alter the fate of matter nearing a singularity? It can tear apart clouds that would have been swallowed whole, or it can whip material into a frenzy, accelerating it to incredible speeds just before the final plunge. This magnetic mediation is the critical prelude to one of the most energetic events since the Big Bang, a flash of light so intense it can outshine a galaxy for a brief, brilliant moment. That brilliant flash outshines entire galaxies in a heartbeat. Gamma-ray bursts are the universe's most powerful explosions, cosmic beacons signaling the violent birth of a new singularity. For a few fleeting seconds, these events release more energy than our Sun will emit across its entire 10 billion-year lifetime. The discovery of these bursts was a complete accident. In the late 1960s, American Vera satellites, designed to monitor for clandestine nuclear weapons tests, detected mysterious pulses of gamma rays coming from deep space, not from Earth. This serendipitous finding opened an entirely new window onto the most extreme physics in the cosmos. Astronomers like Stan Woosley later realized these events were not all the same. They fall into two broad categories, long and short, each with a distinct origin story tied to the creation of the densest objects in existence. Long gamma-ray bursts lasting more than 2 seconds are the death cries of massive, rapidly rotating stars. As such a star collapses into a supernova, its core does not simply form a neutron star. Instead, it immediately plunges past that limit, creating a newborn black hole. The infalling matter forms a torus, a donut of superheated material, and the black hole's immense spin and magnetic fields launch twin jets of plasma outward at nearly the speed of light. These jets, drilling through the outer layers of the dying star, are the source of the intense gamma-ray flash we observe. Short gamma-ray bursts, lasting less than 2 seconds, have a different but equally violent origin. They are the product of two ultra-dense objects, like neutron stars or a neutron star and a black hole, finally merging after a billion-year orbital dance. When these objects collide, they can form a black hole almost instantly, surrounded by a brief, dense torus of leftover neutron-rich material. The same jet mechanism activates, firing a beam of high-energy radiation into the void. The initial gamma-ray flash is just the beginning of the story. As these relativistic jets plow into the tenuous gas of interstellar space, they create a spectacular afterglow that can be observed for days or even weeks. This fading light, visible across X-ray, optical, and radio wavelengths, acts like a cosmic crime scene investigation. By studying the afterglow, astronomers can determine the burst's distance, the energy involved, and the nature of the environment that hosted this cataclysmic event. The most definitive confirmation of this model came with an event that shook the astronomical world in 2017. The short gamma-ray burst designated GRB 170817 was detected just 1.7 seconds after gravitational wave observatories felt the ripples from a neutron star merger. For the first time, we not only heard the universe's gravitational chirp, but also saw the brilliant flash of light and the subsequent kilonova that forged heavy elements like gold and platinum. This single event tied together multiple branches of astrophysics, confirming that neutron star mergers are indeed the engines behind short gamma-ray bursts. Because their light can travel across the universe, these bursts also serve as probes of the early cosmos. The most distant gamma-ray bursts we have observed come from a time when the universe was less than 1 billion years old, allowing us to study the conditions of the first stars and galaxies. The Swift and Fermi space telescopes are our dedicated sentinels, constantly scanning the skies for these fleeting, brilliant signals. Each detection peels back another layer of mystery, revealing the fundamental connection between the birth of singularities and the most powerful explosions since the Big Bang. What these brilliant flashes ultimately illuminate is a much colder, fainter echo from an even more ancient time, a remnant glow that holds the secret to the universe's own singular beginning. This faint glow is the oldest light in the universe, a cosmic fossil from its fiery birth. The cosmic microwave background radiation is the cooled remnant of the Big Bang's initial fireball, a snapshot of the cosmos when it was just 380,000 years old. Before this moment, the universe was a hot, opaque plasma, too dense for light to travel freely. As it expanded and cooled, protons and electrons combined to form neutral atoms, allowing the first photons to stream across space. These particles have been traveling for 13.8 billion years, and we can still detect them today as a uniform microwave hiss that fills the entire sky, a background radiation with a temperature of just 2.7 degrees above absolute zero. Its discovery in 1965 by Arno Penzias and Robert Wilson was a monumental accident. They were troubleshooting persistent noise in a giant radio antenna, and after eliminating every possible source from pigeon droppings to terrestrial interference, realized they had stumbled upon the echo of creation itself. This finding provided the definitive evidence for the Big Bang model, cementing our understanding of an expanding universe with a singular beginning. Later missions, like the COBE satellite led by George Smoot, revealed that this background is not perfectly smooth. It contains tiny variations in temperature, anisotropies that are the imprints of the primordial density fluctuations from which all cosmic structure grew. These minute ripples are the gravitational seeds for everything we see today, the galaxies, the stars, and the supermassive black holes at their hearts. The most detailed map of this ancient light comes from the Planck mission. Its all-sky survey shows the universe in its infancy, with warmer spots representing slightly denser regions and cooler spots representing voids. These patterns align exquisitely with the Lambda CDM model, our standard model of cosmology that includes both dark matter and dark energy. The map is so precise it allows us to measure the universe's age, composition, and geometry with unprecedented accuracy. But the temperature variations are only part of the story. The light of the cosmic microwave background is also polarized, meaning its electric field vibrates in a preferred direction. This polarization carries a record of the universe's dynamics in its first moments. One crucial pattern is the Sachs-Wolf effect, where photons climbing out of gravitational wells, the deep pits of potential energy created by dense matter, lose energy and appear slightly cooler. This effect directly imprints the large-scale gravitational landscape of the young cosmos onto the microwave sky. The most sought-after signal, however, is a specific swirl pattern in the polarization known as B modes. These could be the smoking gun for cosmic inflation, the period of exponential expansion in the universe's first fraction of a second. Primordial gravitational waves, generated during this violent inflationary epoch, would have left their unique twisted signature on the CMB. Detecting this signal would provide a direct window into the energy scales of the Big Bang Singularity itself, telling us what powered the universe's birth. So, how does this ancient echo inform our understanding of that initial singularity? The cosmic microwave background is the ultimate boundary condition. Its remarkable uniformity and specific fluctuation pattern strongly suggest that our universe did not erupt from a chaotic, random singularity, but from one governed by a process like inflation, which stretched and smoothed the cosmos into the state we observe. It constrains our models, forcing us to ask what could have come before this seemingly orderly beginning. If the Big Bang was the ultimate beginning of time, what would its opposite look like? This question naturally pulls our gaze toward the theoretical mirror of a black hole, a white hole where time and expulsion might run in reverse. A fountain of matter and energy erupts from a single point, a cosmic geyser that cannot be entered, only observed from afar. This is a white hole, the theoretical reverse of a black hole singularity. Where a black hole pulls everything in past an event horizon, a white hole would violently expel everything from a central point, creating a one-way boundary that nothing can cross from the outside. It is a solution to Einstein's own equations of general relativity, a mathematically valid mirror image of a black hole, running the film of gravitational collapse in reverse. Physicist Igor Novikov championed the idea that such an object could form one half of a wormhole, with the black hole acting as the entrance and the white hole serving as the exit in some distant part of the cosmos. In this view, the matter falling into a black hole might not end at a crushing singularity, but could instead be spewed out from a white hole, perhaps even in another universe or a different time. Yet for all its mathematical elegance, a white hole faces a profound problem: stability. Our universe seems to run on a one-way street described by the second law of thermodynamics, which states that disorder or entropy always increases. A stable white hole, eternally emitting energy without ever absorbing anything, appears to violate this fundamental cosmic rule. It would be like a fire that only emits heat and light but never consumes fuel, a perpetual motion machine that the laws of physics seem to explicitly forbid. Because of this, most scientists consider white holes physically impossible in our current universe. But what if they are not eternal? Quantum gravity models suggest a fascinating possibility. A black hole that has been evaporating for eons through Hawking radiation might not simply vanish. Instead, at the very end of its life, when its mass has dwindled to nearly nothing, the remnant could undergo a quantum transition, rebounding as a short-lived white hole in a final, explosive burst. This transformation would solve the entropy problem, as the white hole is not a perpetual source of energy, but merely the final stage of a black hole's life cycle. Such an event could be spectacular. Some astronomers have speculated whether certain unexplained, incredibly high-energy cosmic outbursts, particularly those short gamma-ray bursts that lack any visible source galaxy or accompanying supernova, could be the death throes of ancient primordial black holes. Imagine detecting a flash of energy that appears from absolutely nowhere, with no accretion disk, no binary companion, no visible cause at all. This would be a candidate for a white hole event, a singular eruption challenging our understanding of cause and effect. If a white hole truly is the other end of a black hole tunnel, then entering a black hole today could, in theory, mean exiting a white hole in the distant past. This immediately shatters the principle of causality, creating the same grandfather paradox we encountered with wormholes. How could an effect precede its own cause? The existence of white holes forces us to confront whether our linear perception of time is merely a local phenomenon, not a universal law. While we have never confirmed a white hole, the very concept stretches the fabric of reality, suggesting that singularities might not be mere endpoints, but could be gateways connected by a deeper holographic code. A three-dimensional world might be a perfect illusion, projected from a two-dimensional surface like a cosmic credit card chip. This is the holographic principle, a revolutionary idea that suggests our universe, in all its rich depth, could be encoded on a distant, flat boundary. The spark for this came from an unexpected place: black hole thermodynamics. Jacob Bekenstein first proposed that a black hole's entropy, its measure of disorder, is proportional to the area of its event horizon. Stephen Hawking refined this, showing that this entropy is precisely 1/4 of the horizon's area in Planck units. This was bizarre because in everyday physics, entropy relates to volume. A box has more places to hide disorder if it's bigger in all three dimensions. But for a black hole, the maximum amount of information it can contain is dictated not by the volume inside, but by the area of its surface. It is as if all the data describing every star, planet, or astronaut that ever fell in is painted onto the event horizon, stored in tiny, Planck-sized pixels. Physicists Gerard T. Hooft and Leonard Susskind took this clue and ran with it, arguing that this was not just a black hole quirk, but a fundamental property of the universe. The holographic principle boldly states that a description of all the physics within a volume of space can be perfectly encoded on its lower dimensional boundary. This is not a metaphor for a simulation, but a potential statement about the true nature of reality, deeply tied to string theory and a specific mathematical framework known as the AD-SCFT correspondence. This correspondence provides a powerful dictionary, translating intractable problems in a theoretical space containing gravity into more manageable problems in a quantum field theory living on its boundary without gravity. This tool has even found unexpected uses, helping condensed matter physicists model the bizarre behavior of strange metals, materials where electrons behave more like a collective soup than individual particles. So what does this mean for the terrifying singularity at a black hole's heart? Holography suggests it might be an illusion. The true, fundamental description of the black hole is the quantum information dancing on its event horizon. The crushing infinite density we predict with general relativity could be a mathematical artifact, a sign that we are using the wrong language to describe a system that is, at its core, an information processor. The falling astronaut is not lost in a singularity, but their information is translated, scrambled, and stored on the horizon's surface. This elegantly sidesteps the information paradox, preserving the data of what fell in, even if it is hopelessly encoded. Holography redefines singularities not as places where physics ends, but as information structures where our classical understanding breaks down and a deeper quantum description must take over. This profound link between information, entropy, and the fabric of space itself forces us to ask how deeply thermodynamics is woven into the cosmos, guiding us toward a universe where even gravity might be an emergent consequence of a more basic, information-based reality. A black hole glows with heat. This astonishing discovery rewrote the laws of physics, transforming our view of these cosmic voids from cold, simple traps into complex thermal objects brimming with entropy. The journey began when Jacob Bekenstein made a radical proposal. He argued that a black hole must possess entropy, a measure of its hidden disorder, and that this entropy was not tied to its volume but to the surface area of its event horizon. This was a profound break from tradition, suggesting that the maximum information a black hole could contain was painted onto its two-dimensional boundary, not stored within its three-dimensional interior. Stephen Hawking initially disliked this idea, as it seemed to violate a core principle that nothing could escape a black hole. But when he applied quantum mechanics to the curved spacetime around the horizon, he found something miraculous. The black hole was not completely black. It could emit a faint glow of particles, now known as Hawking radiation. This radiation gives the black hole a precise temperature, cementing its status as a thermodynamic entity. The laws governing this system are a direct mirror of classic thermodynamics. The first law links energy, rotation, and charge to changes in the horizon's area, just as traditional laws link heat and work. The second law, however, holds a terrifying cosmic consequence. It states that the combined entropy of a black hole and its surroundings always increases. This means black holes are the universe's ultimate sinks of order, and their growth drives the cosmos toward greater disorder. Hawking radiation emerges from the chaotic quantum sea of empty space. Every moment, pairs of virtual particles flicker in and out of existence. Near the event horizon, one particle can fall in while the other escapes, stealing a tiny amount of the black hole's mass and carrying it away as radiation. Over unimaginable eons, this process causes the black hole to slowly evaporate, shrinking until it potentially vanishes entirely. This evaporation creates the information loss problem. If the black hole disappears, what happens to all the information about the stars and gas it consumed? Quantum physics says information cannot be destroyed, yet Hawking's early work suggested it was. This paradox forced physicists like Leonard Susskind and Gerard T. Hooft to develop the holographic principle, suggesting the information is stored on the horizon. Don Page later calculated how this information might leak back out, describing the Page curve, a graph of the black hole's entropy that rises, peaks, and then falls as the hole evaporates and information escapes. We do not have to look only to the stars to test these ideas. In laboratories, physicists create analog black holes using sound waves in superfluid fluids. By flowing the fluid faster than the speed of sound, they create an acoustic event horizon, a point of no return for sound waves. Just like a gravitational black hole, this sonic horizon emits a thermal glow of phonons, the sound wave equivalent of Hawking radiation. These experiments provide tangible evidence that the underlying physics is real. So what is the ultimate fate of a singularity according to this thermodynamic view? As a black hole evaporates to its final moments, the interplay between information preservation and relentless radiation leads to an extreme proposal, the Firewall Paradox. This suggests that the event horizon might not be a smooth gateway after all, but a searing wall of energy that violently protects the laws of quantum mechanics. The cold void is not so cold, and its heat points toward a quantum extreme that could redefine the singularity itself. An astronaut crossing the event horizon should feel nothing, according to Einstein. Yet quantum physics demands a wall of fire. This is the Firewall Paradox, a brutal contradiction that could incinerate our most basic assumptions about reality. Proposed by physicists including Ahmed Almary, this idea suggests the event horizon is not a smooth gateway but a searing boundary of high-energy particles, a last line of defense for the laws of quantum mechanics. The core of the problem lies in a quantum principle called the monogamy of entanglement. Imagine two particles are intimately linked, their fates intertwined. They cannot share that deep connection with a third party. Now consider Hawking radiation. For the radiation escaping the black hole to be pure and carry no hidden information, the particle pairs created at the horizon must be entangled with each other. But for the information about what fell into the black hole to be preserved, as quantum mechanics requires, one of those particles must also be entangled with the interior. This creates a quantum love triangle, a violation of monogamy. The firewall is the proposed solution, a violent severing of the original entanglement that burns anything crossing the horizon to a crisp, thus preserving the purity of the outgoing radiation and the information it carries. This paradox forces physicists to choose between the smooth spacetime of general relativity and the unbreakable rules of quantum information. Not everyone accepts such a drastic conclusion. Leonard Susskind proposed black hole complementarity, a mind-bending concept where both stories are true depending on your perspective. From the viewpoint of an outside observer, the astronaut is vaporized at the horizon, their information smeared onto the surface. But from the astronaut's own frame of reference, they pass smoothly into the black hole's interior. Both descriptions are valid, complementary truths, avoiding the need for a firewall by accepting that no single observer can see the whole picture. String theory offers another escape route with the fuzzball. In this model, the black hole has no sharp event horizon or central singularity. Instead, it is a giant, tangled ball of strings, a fuzzy, quantum structure that extends to where the horizon would be. An astronaut falling in would simply merge with this fuzz with no dramatic wall of fire, and all information remains preserved within the complex stringy mess. The debate over these solutions is anything but academic. It represents a fundamental schism in theoretical physics, a community grappling with a puzzle that has no clear consensus. The very existence of a firewall would mean that our classical picture of space-time fails dramatically at the horizon, not just at the singularity. If such a violent boundary does exist, could we ever detect its effects? This question turns our attention to the smallest and most ancient black holes, relics from the universe's first moments that might still be lurking in the dark, their tiny horizons potentially revealing the true nature of this quantum inferno. A miniature black hole could be hiding in our solar system right now, a cosmic fossil from the universe's violent birth. These are not the ghosts of dead stars, but primordial black holes forged in the extreme density of the cosmos' first moments. When the infant universe was a seething, hot soup of matter and energy, tiny regions of overwhelming density could have collapsed directly under their own gravity, stitching singularities into the very fabric of spacetime. Their existence was first contemplated by Stephen Hawking and others, who realized these objects would be relics of a time before the first stars even flickered to life. Unlike their stellar cousins, primordial black holes are defined not by their mass but by their origin. They could be as light as a mountain yet as small as an atom, or as massive as a star yet formed without a supernova. Their formation would have been a direct result of the wild fluctuations following the Big Bang, a snapshot of the universe's raw, chaotic power. To find them, we must listen for their subtle effects. A primordial black hole passing between us and a distant star would act as a gravitational lens, bending the starlight and causing the star to temporarily brighten, a phenomenon called microlensing. Surveys like the optical gravitational lensing experiment have scanned millions of stars for just these fleeting flashes, placing strict limits on how many of these dark wanderers could exist. The cosmic microwave background provides another clue, as these ancient black holes would have subtly disturbed the plasma of the early universe, leaving faint scars on the oldest light we can see. Their potential role is staggering. Could these invisible specks be the elusive dark matter that holds galaxies together? It is a tantalizing idea that the missing mass of the cosmos is actually a swarm of countless singularities. Yet observations have largely ruled out primordial black holes as the sole component of dark matter across most mass ranges, though specific windows remain open. Their influence may be more dynamic. A primordial black hole could have been the seed for a supermassive black hole, its immense gravity acting as an anchor around which a galaxy would eventually form. Even more provocatively, some of the black hole mergers detected by LIGO could have involved primordial black holes from the dawn of time. The gravitational wave signal from such an event would carry the signature of a history untethered from stellar life cycles. How would our understanding of a singularity change if we knew they were as common as stars, or even more so? It suggests that the fabric of reality is perpetually punctured by these tiny tears, that singularities are not rare cosmic monsters but fundamental features of existence. This vision of the early universe, dotted with singularities from its very first moments, forces us to reconsider what else might have formed in that primordial crucible. A star in the early universe could have shone with a light not of fusion but of annihilation. This is the dark star, a colossal object powered by the self-destruction of dark matter particles at its core. Imagine the first structures in the cosmos, vast halos of dark matter pulling in hydrogen and helium gas. Within these halos, dark matter particles, possibly weakly interacting massive particles, or WIMP, would collide and annihilate, converting their mass directly into energy. This process would generate immense heat and outward pressure, halting the gravitational collapse needed for nuclear fusion to ignite. The star would not burn, it would glow with the steady, radiant heat of this exotic fuel. Proposed by physicists like Catherine Fries, this mechanism could create stars of almost unimaginable scale. A dark star could grow to be millions of times more massive than our Sun and billions of times brighter, a true leviathan of the early cosmos. Its lifespan would be dictated by the dark matter fuel supply in its core. As it consumed this fuel, or if dynamical friction ejected the dark matter from its center, the support would vanish. The star would then undergo a catastrophic gravitational collapse, falling directly into a supermassive black hole without the intermediary stage of a supernova. This offers a compelling alternative for how the supermassive black holes powering early quasars formed so quickly after the Big Bang. How could we ever find such a phantom star? Their unique power source would give them a distinct signature. They would be exceptionally bright in the infrared part of the spectrum, and their light would lack the specific chemical fingerprints of fusion-powered stars. The James Webb Space Telescope is our most powerful tool in this search. Astronomers are meticulously scanning its deep field data for high redshift objects that are unusually bright and large, yet show spectra that defy conventional stellar models. Finding even one candidate would revolutionize our understanding of cosmic structure formation. Could these dark giants be the primordial seeds from which all supermassive singularities grew? This profound possibility links the invisible world of dark matter directly to the most luminous beacons in the young universe, guiding our search toward the even more fundamental energy woven into the vacuum of space itself. Empty space itself holds a secret power. The vacuum of the cosmos is not truly empty, but a seething quantum sea where virtual particle pairs constantly flicker into existence and annihilate in a heartbeat. This frantic activity gives rise to a background energy permeating every cubic centimeter of the universe, a force known as vacuum energy. It is this pervasive pressure that acts as the engine for cosmic acceleration, pushing galaxies apart at an ever-increasing rate. Albert Einstein first glimpsed this concept when he introduced the cosmological constant into his equations of general relativity, a term he later called his greatest blunder, but which has returned as a cornerstone of modern cosmology. This energy directly influences the grand architecture of the cosmos, shaping the gravitational wells around supermassive black holes and dictating how matter flows toward these singularities. Yet it presents one of the most baffling problems in all of physics. The theoretical value for vacuum energy, calculated using quantum field theory, is a staggering 120 orders of magnitude larger than what we observe. This discrepancy, highlighted by Nobel laureate Steven Weinberg, is the cosmological constant problem, a glaring sign that our understanding of the quantum vacuum and gravity is profoundly incomplete. How could the energy of empty space be so perfectly tuned to allow for our existence? This fine-tuning is so precise that if the value were only slightly different, the universe would either have ripped itself apart immediately after the Big Bang or collapsed back in on itself long before galaxies could form. The influence of vacuum energy extends even to the life cycle of black holes. The Hawking radiation that slowly evaporates a black hole originates from this very quantum activity at the event horizon, where virtual particles are ripped apart, one falling in and the other escaping. The relentless expansion driven by vacuum energy also dictates the ultimate fate of these cosmic giants. ensuring they will one day drift into isolated darkness as the universe cools. An even more unsettling possibility is that our vacuum is not in its true lowest energy state, but is instead a false vacuum. Our universe could be existing in a precarious, metastable bubble. A quantum fluctuation could someday trigger a catastrophic decay, a process known as false vacuum decay. This event would create a bubble of true vacuum that expands at the speed of light, rewriting the laws of physics and erasing everything in its path, potentially triggering a new Big Bang in an instant. Our measurements of this mysterious force come from observing distant supernova, whose unexpected dimness revealed the accelerating expansion, and from precise data from the Planck satellite, which tightly constrained the density of dark energy, strongly supporting our standard model of cosmology, the lambda-CDM model. So how does this omnipresent energy interact with the absolute nothingness of a singularity? It suggests that even at the point of infinite density, the quantum frenzy of the vacuum must play a role, perhaps governing the final moments of a black hole's evaporation or the stability of a wormhole throat. This profound connection between the energy of nothing and the densest points of something guides us toward an even stranger state of matter, one that breaks a fundamental symmetry of time itself. A new form of matter breaks the most fundamental symmetry of all. It oscillates in a perpetual, repeating cycle without ever consuming energy, defying the intuitive flow of time itself. These are time crystals, a bizarre phase of matter first proposed by Nobel laureate Frank Wilczek. Unlike conventional crystals, which have atoms arranged in a repeating pattern in space, a time crystal's structure repeats in time. Its atoms oscillate in a predictable, stable rhythm forever, even in their ground state, their state of lowest energy. This perpetual motion is not a violation of thermodynamics, as it does no work, but it does break what physicists call time translation symmetry. In a normal system, the laws of physics look the same at every moment in time, but a time crystal picks a preferred beat, a specific rhythm that defines its existence. This exotic behavior is thought to be possible only in the most extreme environments, where the fabric of spacetime is warped beyond recognition, such as in the chaotic gravitational fields near a singularity. The key to a time crystal is its discrete time symmetry. Imagine a clock that ticks not because you wind it, but because its very nature is to tick. It returns to its original state only after a specific number of oscillations, creating a robust rhythm that is immune to small disturbances. This robustness is what makes them so tantalizing for quantum computing. The fragile quantum states used in qubits, the building blocks of quantum computers, are notoriously prone to decoherence, collapsing from the slightest environmental noise. A time crystal's inherent stability could act as a perfect quantum memory, protecting information within its unending rhythm for vastly longer periods. We have already created primitive time crystals in laboratories. Scientists have used systems of trapped ions, holding them in place with electromagnetic fields and nudging them with lasers to initiate the telltale oscillation. Other experiments have utilized the subtle quantum spins of atomic impurities in diamonds, known as nitrogen vacancy centers, to observe this broken symmetry in time. The great challenge is maintaining the quantum coherence of these systems, keeping the delicate synchronized dance from falling into discord. The potential applications extend far beyond computing. One profound illustrative example involves using time crystals to probe the nature of thermal equilibrium in black hole analogs. Just as a black hole is theorized to have a specific temperature, these analog systems can be studied to see how they thermalize or reach a uniform temperature. A time crystal, forever oscillating and never reaching a true thermal equilibrium, could be used to test these limits, acting as a precise tool to investigate how information behaves at the edge of an event horizon. Could the distorted spacetime around a singularity naturally give rise to such temporal structures? If so, then time crystals would be more than a laboratory curiosity. They would be a fundamental feature of the most violent places in the cosmos, a rhythmic pulse in the heart of chaos. This deep connection between time, matter, and information inevitably draws us into the most mysterious linkage in the universe, the spooky bond of quantum entanglement. Two particles can become a single entity, their fates linked across the universe in a bond that defies space and time. This is quantum entanglement, a phenomenon so strange that Albert Einstein himself called it spooky action at a distance. Once two particles are entangled, a measurement performed on one seems to instantaneously influence the state of the other, no matter if they are a millimeter or a million light-years apart. For decades, this was seen as a philosophical curiosity, but the brilliant physicist John Bell devised a practical test, a set of inequalities that could prove whether this spooky connection was real. When experiments were finally performed, they confirmed it. Entangled photons created in a lab behaved as a single system. Their outcomes correlated in ways that no local, hidden theory could ever explain. This non-local connection is not a flaw in our understanding. It is a fundamental feature of the quantum world, and it may be the key to unlocking the deepest secrets of black holes. The event horizon of a black hole might be threaded with a web of entanglement between the particles just outside and the quantum states inside. This entanglement entropy, a measure of the quantum connections across the boundary, is directly related to the horizon's area, providing a profound link between information and gravity. This idea is taken to its ultimate extreme in the ER equals EPR conjecture, a proposal from physicists like Leonard Susskind and Juan Maldacena. It suggests a breathtaking equivalence that two entangled particles are, in fact, connected by a microscopic wormhole, an Einstein-Rosen bridge. In this view, entanglement does not just describe a connection, it physically weaves the fabric of spacetime itself. The spooky action at a distance is not magic. It is the manifestation of a tiny, submicroscopic tunnel in the geometry of the universe. This has direct implications for the information paradox. When two black holes become entangled, the conjecture suggests a wormhole forms between them, creating a bridge that could preserve information in a way that satisfies both quantum mechanics and general relativity. Quantum teleportation, a process where the state of a particle is transmitted using an entangled pair, relies on this same non-local resource. It does not move the physical particle, but instantly transfers its quantum identity, a feat that underscores how information itself can transcend classical limits. The mathematics behind this is captured in the holographic entanglement entropy formula, which allows physicists to calculate the entropy of a region by finding the area of the smallest possible surface that could contain it within a higher dimensional space. This is not just abstract math, it is a potential blueprint for reality, suggesting that the geometry of space emerges from a vast, underlying network of quantum links. So how does this intricate web of entanglement behave when stretched and warped near a singularity? It may be the very glue that holds spacetime together, preventing it from tearing completely apart under infinite curvature. This exploration of how quantum connections shape cosmic structures leads us to consider even more exotic remnants of the early universe, the cosmic strings and topological defects that could be frozen into the fabric of everything. These cosmic threads are thinner than a proton yet denser than a mountain range. They are cosmic strings, hypothetical scars left over from the universe's fiery infancy, when the fundamental forces of nature split apart in a process known as symmetry breaking. When the cosmos cooled, its underlying fields could not settle into a perfectly uniform state everywhere. In some regions, the field configurations became tangled, locking into stable, one-dimensional flaws in spacetime itself. These are topological defects, and a cosmic string is one such relic, a crack in the cosmic ice. Proposed by physicist Tom Kibble, these strings are not made of atoms, but of pure energy, twisted and frozen into the fabric of reality during the first fleeting moments after the Big Bang. Their properties are almost unimaginable. A single cosmic string might be infinitely long, or form loops stretching across galactic distances, and its tension is so immense that just a kilometer of string could outweigh our entire planet. This incredible mass density gives them a ferocious gravitational pull. As they oscillate and vibrate at near light speed, they would whip the spacetime around them, generating ripples in the fabric of the cosmos. These are gravitational waves, a constant, faint hum from the string's eternal dance. Their gravity is so extreme that it bends light, creating a unique signature. A cosmic string passing between us and a distant galaxy would not just magnify its light like a typical gravitational lens. It would create a perfect double image, a sharp line of twin galaxies with no distortion in between. This is because the spacetime around a string is conical, like a pencil tip poking through paper, warping geometry without curving it. Astronomers search for these telltale duplicates in deep sky surveys, and they also scour the cosmic microwave background for the distinctive, linear temperature shifts a moving string would imprint on the ancient light. The influence of these strings could be foundational. In the early universe, a network of cosmic strings would have acted as a gravitational scaffold. Their immense density would have pulled ordinary matter into dense filaments, seeding the first clouds of gas that collapsed to form the very first stars and galaxies. Some theories even suggest that the loops of string themselves could have directly collapsed, their gravity so intense that they pinched off into primordial black holes without the need for a stellar supernova. This provides a potential bridge between the largest cosmic structures and the smallest singularities. Their dramatic nature might also explain fleeting, powerful events. The immense energy released when a string loop snaps or when two strings intersect could be the engine behind mysterious fast radio bursts, those brilliant, milliseconds-long flashes of radio energy from deep space. The crack of a cosmic whip could echo across the cosmos. If such fundamental flaws are woven into reality, could they be tied to structures even more alien than singularities? The existence of cosmic strings naturally pulls our curiosity toward realms beyond our three familiar dimensions, where the true nature of such defects might be revealed. Our universe might be a three-dimensional island adrift in a higher dimensional sea. This is the world of brains and extra dimensions, a cornerstone of string theory where the fabric of our reality is a membrane or brain floating within a grander cosmos called the bulk. In this picture, all the particles and forces we know, like light and matter, are stuck to our brain, but gravity, the curvature of spacetime itself, is different. It can leak off our brain and seep into the hidden dimensions, diluting its strength and explaining why it is so astoundingly weak compared to the other fundamental forces. This concept was powerfully explored by physicists like Lisa Randall and Raman Sundram in their RS1 model, which uses a warped extra dimension to create a natural explanation for this vast difference in force strength. If gravity is spreading into these unseen realms, it fundamentally changes the rules for the most powerful gravitational objects in existence, black holes and their singularities. In a universe with extra dimensions, the energy required to create a black hole plummets. the immense gravitational forces needed to crush matter into a singularity in our three-dimensional world become far more achievable if gravity has more room to operate. This raises a startling possibility that we could create microscopic black holes right here on Earth. The Large Hadron Collider, or LHC, slams protons together at nearly the speed of light, concentrating energy in a tiny volume. In a world with large extra dimensions, such a collision might be enough to stitch a tiny tear in space-time, a micro black hole that would evaporate in a flash of Hawking radiation. Scientists at CERN meticulously search for the telltale signature of such an event, a burst of particles that seems to appear from nowhere, carrying away energy that has vanished from our brain into the hidden dimensions. These brain-world black holes would look and behave differently than their standard cousins. Their event horizons might be distorted, stretched into odd shapes by the geometry of the higher dimensional space. Most profoundly, the terrifying singularity at their center could be resolved, smoothed out into a non-singular, finite object once viewed from the full perspective of the bulk. The infinite density that breaks our physics in 3 dimensions might simply be an illusion, an artifact of our limited view from the brain. This search for extra dimensions is not confined to massive colliders. Precise measurements of the gravitational force at microscopic distances, smaller than the width of a human hair, look for any deviation from Newton's familiar inverse square law. If gravity is leaking into another dimension, its strength would change at these tiny scales. So far, no such deviation has been found, placing stringent limits on the size and shape of these hidden realms. This entire framework forces us to confront a profound question about our place in the cosmos. If the properties of our universe, including the number and size of its dimensions, are just one random outcome among a vast multiverse of possibilities, why do we find ourselves in a world so exquisitely tuned for complexity and life? This is the Anthropic Principle, a lens through which we must view the ultimate nature of singularities and the cosmic code they represent. Our universe appears perfectly tailored for life, but this may be a profound illusion. We exist in a cosmos with specific physical constants, from the strength of gravity to the mass of an electron, that seem miraculously fine-tuned. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the cosmological constant were a fraction larger, the universe would have blown itself apart before the first galaxies formed. This observation is the heart of the Anthropic Principle, an idea crystallized by physicist Brandon Carter. It simply states that our observations of the universe are necessarily filtered by the fact that we are here to make them. We could not possibly find ourselves in a cosmos incapable of giving rise to conscious life. The principle comes in 2 forms. The weak Anthropic Principle notes that we must live in a region of the universe, and at a time in its history where conditions are suitable for our existence. The strong version goes much further, suggesting the universe must have properties that allow life to develop at some stage within it. This framework directly connects to the Multiverse Hypothesis. If an infinite number of universes exist, each with different physical laws and constants, then it is no surprise we find ourselves in one of the rare habitable bubbles. The specific nature of our singularities, then, might not be a fundamental law but a local byproduct. In a universe where gravity is too weak, black holes might never form. In one where nuclear forces are different, stars might not forge the carbon essential for life. Our ability to ponder the crushing density of a singularity depends on a long chain of cosmic coincidences that produced carbon-based observers. Critics argue this line of reasoning is a cop-out, a non-predictive argument that explains everything and therefore nothing. Yet, it finds a powerful illustrative example in the mass of the Higgs boson. Its value is peculiarly low, a puzzle known as the hierarchy problem. While some physicists hope for a deeper scientific explanation, others propose an anthropic one. In the vast landscape of possible universes, only those with a Higgs mass in a narrow range would allow for stable atoms, chemistry, and ultimately, us. So, does this mean singularities are an inevitable feature of any life-bearing cosmos? It seems likely. The same stellar furnaces that create the carbon in our bodies are also the factories that end their lives as black holes. The cosmic cycles that produce the heavy elements for planets and life are driven by the violent gravitational collapses that birth singularities. Our existence is inextricably linked to the same destructive processes that power these cosmic mysteries. This reflection on our own place in the cosmos naturally guides us toward the next great frontier, the future tools and theories that will push our understanding of these enigmatic hearts even further. Our next great telescopes will not just see deeper into space, they will peer further back in time to the very edges of reality itself. These are not mere upgrades, but entirely new senses for humanity, instruments like the James Webb Space Telescope and the upcoming Square Kilometre Array. They are designed to detect the faintest whispers from the early universe, potentially capturing the indirect signatures of singularities at work. The Event Horizon Telescope, which gave us our first ghostly image of a black hole's shadow, is already expanding into a more powerful global network. Its next targets could reveal the dynamic, churning plasma around a black hole in real time, showing us how these cosmic engines devour matter and fire jets of energy across thousands of light years. Astronomers like Priyamvada Natarajan are using advanced simulations to predict what we might see, creating digital laboratories that model the violent dance of matter at the event horizon. These virtual black holes then guide the observational strategies of the actual telescopes, telling them precisely where and when to look for the subtle warping of light or the telltale flicker of hot gas. To listen for the low-frequency hum of the cosmos, we are sending an observatory into space, the LISA mission, a fleet of 3 spacecraft flying in a perfect triangular formation millions of miles apart, will form a gravitational wave antenna larger than the Sun. It will be tuned to the mergers of supermassive black holes, events so colossal they shake the fabric of spacetime for billions of years. By measuring these ripples, LISA could test whether the event horizons of these merging giants behave exactly as Einstein predicted, or if they reveal the fuzzy, quantum nature of spacetime itself. On the ground, giants are rising. The 30-meter telescope and the extremely large telescope will have such immense resolving power they could watch individual stars whipping around our galaxy's central black hole, Sagittarius A star, mapping its gravitational field with unprecedented precision. They might even detect the faint, theoretical glow of Hawking radiation from nearby small black holes, a signal that has so far eluded all our efforts. The sheer volume of data from these instruments is beyond human capacity to process alone. Artificial intelligence now sifts through this cosmic noise, learning to identify the subtle patterns that signal a distant black hole merger or a newborn singularity. This effort is so vast it has become a global endeavor, with international collaborations pooling resources and intellect. Citizen scientists can join the search from their own homes, helping to classify strange new objects in galaxy surveys, proving that the quest to understand the universe is a fundamental human drive. What will these new eyes and ears finally reveal? They may show us that the stark black hole shadows we see are not the final word, but merely the silhouette of a deeper, more complex quantum structure. They could capture the birth cry of a primordial black hole, or find evidence that our universe's expansion is driven by the vacuum energy of countless microscopic singularities bubbling in and out of existence. Each new observation brings us closer to answering the most profound questions, forcing us to confront not just the physics of these objects, but the very meaning of reality and our place within it. A single misstep could unravel the fabric of space around us. This is the profound ethical weight that comes with our growing understanding of singularities, a power that demands we question our responsibilities. The theoretical ability to harness a black hole's energy, perhaps through a Penrose process where we extract rotational energy from its ergosphere, presents a staggering possibility. Imagine a future civilization drawing power from a controlled singularity, fueling entire star systems. Yet this same power source, if mismanaged, could become an unstoppable cosmic weapon or an accidental gravitational vortex, consuming everything in its path. Philosophers and scientists like Nick Bostrom have long warned of such existential risks, where advanced knowledge outpaces our wisdom. The very act of probing these mysteries could trigger unforeseen consequences, altering the fundamental constants that make our reality stable. This is not distant speculation. The debate around the Large Hadron Collider grappled directly with these fears. Before its activation, a global team of physicists conducted rigorous safety assessments, calculating the probability that its high-energy collisions might create a micro-black hole. Their conclusion was that such an event was incredibly unlikely, and that any microscopic black hole would evaporate instantly via Hawking radiation, posing no threat. But the public concern was real, highlighting a crucial divide between scientific curiosity and public apprehension. Who gets to decide when an experiment is too risky? The question of international regulation becomes paramount. No single nation should hold the power to manipulate space-time without oversight. Global treaties, similar to those governing nuclear non-proliferation, may be necessary to govern future research into gravitational manipulation and the creation of artificial singularities. This necessitates transparent public engagement, moving complex science from secluded laboratories into community dialogues. Beyond the immediate physical risks lies a deeper cultural impact. How would humanity's self-perception change if we discovered evidence of a singularities engineered by an extraterrestrial intelligence? Such a finding would shatter our cosmic loneliness, suggesting that other civilizations have not only survived their technological adolescence, but have mastered the forces of creation itself. It could inspire a new era of cosmic cooperation, or it could instill a profound fear, a sense of technological inferiority in a dangerous universe. The ethical landscape here is a delicate balance between our innate curiosity and a necessary caution. Our drive to understand the cosmos is what propels us forward, yet the power inherent in singularities requires a humility we are still learning to cultivate. How do we ensure that our quest for knowledge does not become the instrument of our own undoing? This reflection on our cosmic responsibilities leads us to the most personal of all inquiries, a philosophical examination of what these discoveries say about our own fleeting existence. Staring into the abyss of a singularity forces us to question the very nature of our own consciousness. How can a mind evolve to navigate a world of trees and predators possibly comprehend a point where time stops and space becomes meaningless? The philosopher Immanuel Kant argued that our perception is bound by the fundamental categories of space and time. We are like creatures in a cave, only able to see the shadows of reality cast upon the walls of our own senses. A singularity shatters those walls. It represents a place where our innate tools for understanding simply fail, a raw confrontation with the absolute limits of human knowledge. This is what Thomas Nagel meant when he asked what it is like to be a bat, We can study a bat's sonar, but we can never truly know the subjective experience of perceiving the world through sound. Similarly, we can write the equations for a singularity, but we can never grasp the reality of existing outside of time. Is this point of infinite density absolute nothingness, a true void, or is it a gateway to another layer of existence, a cosmic loom weaving new realities from the unraveled threads of our own? This ambiguity strikes at the heart of causality. If time itself breaks down, then the chain of cause and effect, the very logic that governs our universe, unravels. Does this mean our lives are not a linear path determined by past events, but something far more fluid? The existence of singularities challenges the illusion of free will, suggesting that at the most fundamental level, the universe may not operate on a predictable, clockwork mechanism. Our sense of choice might be a beautiful, complex emergent property of a reality whose bedrock is pure potential. This leads to a profound connection between mind and cosmos. Could our own consciousness be a localized expression of the same fundamental properties that govern a singularity, a tiny knot of self-aware spacetime? Some interpretations of quantum mechanics even suggest that the act of observation plays a role in determining reality, intertwining the perceiver with the perceived in a way that makes the cosmos and the conscious mind inseparable partners. This idea spirals into the possibility that our entire universe is a simulation, a vast computation running on a substrate we cannot see. In that view, a singularity might be a bug in the cosmic code, a divide by zero error, or perhaps a backdoor into the programmer's realm. Literature and art have long used the symbol of the void to represent the ultimate unknown, from the terrifying cosmic horrors of H.P. Lovecraft to the majestic Stargate in Arthur C. Clarke's 2001, the singularity serves as a mirror for our deepest fears and grandest aspirations. It is the ultimate blank canvas onto which we project our questions about mortality, purpose, and the nature of existence itself. Accepting a finite or cyclic cosmos, where everything we know is destined for a singularity or born from one, can be existentially dizzying, yet it also imbues our fleeting moment of awareness with profound meaning. We are the universe become conscious, staring back at its own mysterious heart, daring to ask what deeper truths lie hidden within the void. Our journey through the celestial singularity reveals a cosmos far stranger and more wondrous than we ever supposed. We have stood at the edge of black holes, grappled with the paradoxes of quantum information, and traced our own cosmic lineage back to the fiery dawn of the Big Bang. From the theoretical bridges of wormholes to the infinite possibilities of the multiverse, each concept has stretched the very fabric of our understanding, reminding us that the universe is built not on certainty, but on profound mystery. These singularities are not in points, they are the ultimate frontiers of physics, the places where our current knowledge ends and the next great discovery begins. They are an open invitation to question everything we assume about reality. The astronomer Carl Sagan once reflected that somewhere, something incredible is waiting to be known. That incredible something is hidden within these cosmic knots, in the warping of space-time and the birth of new universes. Let this exploration be a starting point for your own curiosity. The next time you look up at the stars, remember the invisible depths between them, the dark hearts of galaxies where time stands still and new physics is being written. We want to hear what captivates you most. Was it the holographic principle, the faint glow of Hawking radiation, or the cosmic cycle of birth and rebirth? Share your thoughts in the comments and continue the conversation. If you are ready for more journeys to the edge of understanding, subscribe and join us as we unravel the next great mystery. Our shared quest for knowledge is just beginning.